So in this module, we will be looking at how to connect memory to the different processors starting from 8088 to the 80486 processor. Memory interfacing, we will talk about how we connect memory to the system buses of these processors. We have already seen how address, data and control signals are going to be generated by the processor and how this becomes the system bus. Now we will see how the memory is going to be connected to the system bus. We'll start with the memory interfacing of 8088. The simple reason is the data bus of 8088 is going to be 8 bits. And generally memory is also byte organized, hence it becomes easier to connect 8088 with the byte organized memory than compared to any of the other processors. 8086 or 286 have a 16-bit data bus, 386 and 486 have a 32-bit data bus, hence the interfacing of memory becomes a little more complicated there. So we'll start with a simple example of how we are going to connect 8088 and then we will move on, have a look at how to connect the other processors. Now whenever we are talking about interfacing, whether it is going to be memory or in the later module when we are talking about I/O interfacing, we are going to be connecting the memory or the I/O devices to the system bus. The system bus is essentially going to be the buffered bus output which we are going to get from the processor. So in case of 8088, we would be having the address lines A0 to A19, which are going to be available through the latches. Now you have to remember that in 8088, it has only a 8-bit data bus. So we are going to have a latch for AD0 to AD7, and we would have a latch for the address lines which are multiplexed with the status signals. So we are going to have A0 to A19. That is the address bus. The system bus also has the control and the data bus. The control signal is again going to be buffered and it's available via a logic circuit where you're going to be connecting the read, write and IO/memory signal into memory read, memory write, IO read and IO write. And of course we are going to be having the data bus which is going to be D0 to D7. So this is going to be the system bus, and what we are going to do is we are going to be connecting the memory or the I/O device to the system bus. So what we are going to see is how to connect memory to the system bus in this particular session, and we are going to concentrate on the 8088 processor. The 8088 processor, the main feature is going to be that it has a 8-bit data bus which is going to be D0 to D7. So at a time it can fetch 8 bits of data from memory or 8 bits of instruction from memory. That is going to be the characteristic of the 8088 data bus. Now whenever we are talking about memory, memory would also have its own address lines. It has its data lines and it has its control signals. Now how many address lines, how many data lines essentially is going to be based upon the size of the chip and the organization of the chip. Now generally whenever we talk about memory, the address bus is going to be used for selecting one of the memory location and the data communication is going to take place via the data bus. So address selects one of the memory location, data communication, either writing data to memory or reading data from memory is going to take place via the data bus. Now when we are talking about a normal 2K memory chip, so when we say it is 2K, we also say it is 2K into 8, meaning that there are 2K memory locations and every memory location can store 8 bits of data. So this is called as a byte organized memory chip. So every location can store 8 bits of data. There are totally 2K locations. The size of this memory chip is going to be 2 kilobytes. Now, if you want to select between 2K locations, you have to select 2K locations. You would be having 11 address lines. Remember that whenever we are talking about an n-bit address, it means that you would be having 2 to the power of n memory locations available. So it follows that if I have 2K memory locations, the number of address lines which are going to be required are 11 address lines. So 2 to the power of 11 is going to be equal to 2K. So you're going to have 11 address lines starting from A0 to A10, because we are counting from 0. It starts from A0 to A10, which are going to be 10 address lines. These address signals are going to be input to the memory. Remember, address bus is output from the processor. It is input to the memory because it has to select one of the memory lines. And memory is going to be byte organized. It has a data bus D0 to D7. You can read data from memory or write data into memory. So evidently this is going to be a RAM chip which allows you to read data as well as write data. So you have the read control signal, which again comes from the processor. The processor tells the memory whether data is going to be read from the memory location or returned into the memory location. So control signals again are going to be coming from the processor. And other than the read and write, there is a very important signal which is called as chip select, which is used for enabling this particular memory chip. So if this memory chip has to work, the chip select signal has to be active. You can see that all the control signals are going to be row active. The read, write and chip select control signals are all low active signals. So it means that this 2K chip must be active. This particular signal has to go low. So we will also see how this chip select signal is going to be generated using the address bus of the microprocessor. So what we are going to be trying to do is we will take it with an example. We are going to see how to interface 2K memory chips. We have 2K memory chips. We need to connect up to 8 kilobytes of memory to 8088. Okay. We have to have an 8088 system which is going to have 8K of memory, and what is available with us are going to be 2K memory chips. So whenever you're doing memory interfacing, you're going to do three different things, or you're going to make three different decisions. You are going to decide on the number of memory chips that would be required. You are going to decide on the memory mapping, or you're going to decide what is going to be the address that is allocated to each chip, what is called as the address space. So what are going to be the set of addresses which are going to be given to each memory chip, and you're also going to design the decoding logic which will be used for selecting these chips. So any interfacing would require that you decide on the number of memory chips. You have to say what address is going to be allotted to which particular memory chip, and then according to the addresses allocated, you also have to design the decoding logic. So first what we do is we create what is called as a memory map. Now let's remember that in this example we are trying to connect 8 kilobytes of memory to the 8088 processor, and totally we are going to be having 2K memory chips available. The chips that are going to be available are 2K chips. 8K of memory has to be connected to 8088. So we'll first look at how the memory mapping is going to be done. So memory mapping would first be that you have to decide on the number of chips. So totally we are going to require 8K of memory. So 8K of memory, and if you have 2K chips available, it means you have to use 4 2K chips. Only then you would get 8K of memory. So 4 chips are going to be connected to 8088. So when you say 8K of memory, it need not be that you have a 8K chip available. You might have a 4K chip available, you might have a 2K, or you might even have a 1 kilobyte memory chip available. Here the memory chip available is going to be 2K. So if you need to connect 8K of memory to 8088, you have to make use of 4 such 2K chips. So if I'm going to have 4 chips, each of them is going to have its own set of addresses. Now you have to remember that you have to allocate addresses to each of the memory chips. So let's assume that these memory chips are all going to be RAM. You can read data, you can write data from these memory chips. So we are going to have 4 memory chips. Let's call them as RAM 1, RAM 2, RAM 3 and RAM 4. Now what we have to do is we have to allocate a set of addresses to each RAM. Now how many addresses you have to allocate? These are 2K chips. So since they are 2K chips, you have to allocate 2 kilobytes of addresses to each memory chip. So if I am going to talk about the first RAM, let's say it is starting from address 000. The last address that is going to be available for this would be 007FF. This is going to be totally 2K addresses which are allocated to RAM1. So RAM1 is going to be activated for any of these addresses starting from 000 to 007FF. Now similarly, you have to allocate a set of addresses for the other RAM chips. So if the first RAM chip is going to be stopping at address 007FF, the next RAM chip would have to start at the next consecutive address, which is going to be 00800. Now again, you have to allocate 2K addresses to this chip because the size of this chip is going to be 2K. So the addresses you're going to allocate is going to be 00FFF. We are starting from 800. The last address would be 0FFF in this case. Now, we have given addresses to 2 of the chips. Again, we have to connect 2 more RAM chips. So the last address of the second RAM chip is going to be FFFF, meaning that the next RAM chip would start from address 01000. So RAM3 will start from address 0100. Again, if you are allocating 2K addresses to it, the last address here is going to be 7FFF. Then let's talk about what will happen in case of the next RAM chip. The next RAM chip would start from address 01800 and it will go up to address 01FFF. So we have 8K of memory starting from address all zeros to address 01FFF. So this 8K of memory is going to be divided between 4 chips. The first 2K of addresses given to RAM1, the second 2K addresses given to RAM2, the next 2K address given to RAM3, and then the last 2K block given to RAM4. So now whenever you are going to be accessing memory, let's say you are going to be accessing some location which is going to be 0800802. So let's say this is going to be the address which you are going to access. So when you are going to access memory at location 0080002, the RAM chip that must be selected must be RAM2. And from RAM2, you are going to read data from the location which is going to be 0080002. For instance, if you are going to access data from location, let's say 01620. So if this is going to be the memory address, then in this case, RAM3 must be selected and you should read data from location 01620 in RAM3. So based on the address, only one of the RAM chips must be selected at a given point of time. So if the address is between the range 000 to 07FFF, RAM1 must be selected. So if the address is going to be from range 0800 to 0FF, RAM2 must be selected. If it is going to be from 0100 to 017FF, RAM3 must be selected. For the next address range, RAM4 must be selected. So at a given point of time, only one memory chip will be selected. Which particular memory chip is going to be selected essentially depends upon the address which you are trying to access. So the first thing that we do when you're doing memory interfacing is you have to find out how many memory chips are going to be required. So we said we have 2K and we need to connect up to 8K of memory. So if you need to connect up to 8K of memory, you will require 4 of these 2K chips. And then you have to allocate a set of addresses to each of these chips. You have to allocate 2K addresses because the size of this chip is going to be 2K. So we have 4 RAM chips and we had allocated the addresses. Now this is called as memory mapping. Allocating a set of addresses to a memory chip is termed as memory mapping. So what we have done is we have mapped our memory. Now we have to see how this memory chips or all the 4 of them are going to be connected to the processor. So when we are talking about the 2K chips, we are going to be having the address lines A0 to A10. We are going to be having the data bus of the CPU, which is going to be D0 to D7. We are going to be using 8088, so there is going to be no problem. You will be connecting D0 to D7 of the memory chip to D0 to D7 of the CPU directly. So there will be no problem. You are going to be using the first 11 address lines A0 to A10. So A0 to A10 of the system bus goes as A0 to A10 here. The write signal of course gets connected to memory write. The read signal gets connected to memory read. So that is simple. Now comes the chip select. Remember, at any given point of time, depending upon the address, only one memory chip must be selected. So we said that if address is going to be in the range 000 to 007FF, then in that case the RAM chip 1 must be selected. So the remaining address lines of the CPU will be used for selecting between RAM 1, RAM 2, RAM 3 and RAM 4. So we will be designing what is called as an address decoding logic, and this is going to be used for selecting the RAM chip. Now the purpose of the chip select signal, as I said earlier, is only when the chip select signal is active, this particular memory chip will be active, or you can make use of the memory chip only when the chip select signal is going to be active. It's a low active signal, so for enabling the memory chip, this chip select signal must be made low. So what we are going to see now is how we are going to be generating, or how we are going to be designing the address decoding logic. Right. So for generating the address decoding logic, we are going to be using a digital device which you're already familiar with. You would have used it in the digital design course. You would have also used it in the labs. This is going to be LS138. LS138 is a 3:8 decoder. It has 3 inputs A, B and C. Based upon these 3 inputs A, B and C, one of the outputs, output 0 to output 7, is going to be active. All the outputs are going to be low active. So this makes it easy to connect to the chip select signal, because remember, your chip select signal is also going to be chip select bar. So it is going to be a low active signal. So you can directly connect the output of the decoder to the chip select signals. So A, B, C are the input. Output 0 to output 7 are going to be the output of the decoder. Based on A, B, C, one of these outputs would be active. There are also going to be 3 enable signals. This is used for enabling the function of LS138. There is going to be G1, which is going to be a high active signal, G2A bar, which is going to be a low active signal, and G2B bar, which is again going to be a low active signal. So if LS138 should function, G1 should be high, G2A bar and G2B bar must be low. Only then LS138 is going to function. Now this gives the truth table of LS138. So these are the enable inputs. These are going to be the select lines. So remember, G1 has to be high, G2A bar and G2B bar have to be low for any of the outputs to be active or LS138 to work. So G1 is high, G2A bar is low, G2B bar is low, and based on ABC, if ABC, all of them are going to be low, output 0 will be low. If it's going to be 001, output 1 is going to be made low. If it is 010, output 2 is going to be made low, and so on. So one of the outputs would be active based upon the combination of A, B and C. So if A, B and C happen to be 101, output 5 is going to be active. So that's how the decoder is going to function. Now we are going to make use of this particular decoder in order to generate the chip select signal of the 4 RAM chips. We have RAM 1, RAM 2, RAM 3 and RAM 4. To generate the chip select signal of RAM 3, RAM 1, RAM 2, RAM 3 and RAM 4, we are going to make use of this LS138. So let's look at the address of the RAM chips a little more closely. We will look at it in the binary format. I'm just showing A0 to A15 because anyway A16 to A19 are all going to be low. We have already seen that A16 to A19 are all going to be low for the RAM chip. So I've just expanded A0 to A15. So A0 to A10 would vary within the RAM chip itself. The lower address is going to be all zeros. The higher address is going to be 07FFFF. So A0 to A10 is used for selecting one of the 2K memory locations within the RAM chip. So we cannot use this for decoding because within the RAM chip itself, these 11 address lines will vary. you have to select one of the 2K locations based on these 11 address lines A0 to A10. And this we have already given to the RAM chip to select one of the 2K locations. We are going to use the rest of the address lines A11 to A15. So if the address happens to be from 000 to 07FF, this is going to be the binary value that you will get. If it is 0800 to 0FFF, this is going to be the binary value. And again, if it is 0100 to 017FF, this shows the binary value of the first address and the last address. And again, 01800 to 01FF, the first binary value and the binary value of the last address. Now, if you're going to look at address lines A0 to A10, we have said that A0 to A10 already goes to the RAM chip to select one of the 2K locations. So we cannot use these 11 address lines A0 to A10. Let's look at the other address lines A11 to A15. So if you're going to look at the other address lines A11 to A15, one thing that you will notice is A13, A14, A15 are going to be 0 for RAM 1 as well as for RAM 2, for RAM 3 and RAM 4. So A13, A14 and A15 are going to be all low for RAM 1, RAM 2, RAM 3 and RAM 4. So this cannot be used for selecting between RAM 1, RAM 2, RAM 3 and RAM 4. To select between RAM 1, RAM 2, 3 and 4, we have to use the lines A11 and A12. So if you look at these lines A11 and A12, these are going to be 00 for RAM 1. You can see it is 01 for the address range of RAM 2, 10 for the address range of RAM 3 and 11 for the address range of RAM 4. So very simply we can say if A11 and A12 both are going to be 0, then RAM 1 will be selected. If it is 01, RAM 2 will be selected. If it is 10, RAM 3 should be selected. If it is 11, RAM 4 should be selected. So these are the address lines which distinguish RAM 1 from RAM 2 and RAM 3 and RAM 4. So we have to use this for address decoding. So how are we going to use this for address decoding? So we have our decoder which is going to be output 0 to output 7. We don't require all the 8 outputs because we have only 4 memory chips, 1, 2, 3 and 4. So these are going to be connected to RAM 1, RAM 2, RAM 3 and RAM 4. And to A, B and C, we are going to be connecting the address lines A11, A12 and A13. If you go back to the address map, this is A13, A12 and A11. You can see that A13 is constantly going to remain 0, whereas A11 and A12 is going to vary according to the RAM chip. So in this case, if the address happens to be within the range 000 to 07FFFF, then in that case, A11, A12 both are going to be 0. A13 will also be 0. So when A, B and C all are going to be low, in that case RAM 1 is going to be selected. So if this is going to be 0, 1, 0 or it's going to be 0, 0, 1, in this case RAM 2 is going to be selected. If it is 0, 1, 0, RAM 3 is going to be selected. If it is 0, 1, 1, RAM 4 is going to be selected. So what we have seen earlier is based on the value of A12, A11, A12 and A13. If all three are going to be 0, then it is RAM 1, 0, 0, 1, it is RAM 2, 0, 1, 0, it is RAM 3 and 0, 1, 1, it is going to be RAM 4. So this can serve as our A, B and C inputs to the decoder. So that is what we have done. We have connected A13, A12 and A11 to A, B and C inputs. Output 0, 1, 2, 3 go to RAM 1, 2, 3, 4 respectively. Now coming to the enable signals. We have to use the enable signals for G2A bar and G2B bar as well as G1. Now we know that the address lines A14, A15 both are always going to remain low irrespective of the RAM chip. So what has been done is A14, A15 both have been connected to G2A bar and G2B bar. So if the address is going to be anywhere in the range starting from 000 to address which is going to be 01FFFF, for all of them the A14 and A15 lines are going to be 00. So since they are going to be 00, G2A bar and G2B bar will be enabled. Now coming to the G1 signal, again we know that A16 to A19 all are going to be 0 for our 4 RAM chips. So since all of them are going to be 0, the output of the NOR gate will be high only when all the inputs are going to be low. So when A16 to A19 all of them are going to be low, the output of the NOR gate is going to be high, so G1 will also be active. So anywhere in the address range starting from 000 to 01FFFF, this particular decoder will be enabled. This decoder is going to be enabled because A14 will be low, A15 is going to be low, as well as A16 to A19, all of them are going to be low. So this is used for enabling the decoder. Now one thing you will notice is we have used all the address lines here. Address lines A0 to A10 are going to be given to the individual RAM chips that we have already shown. A0 to A11 is going to be connected to RAM 1, RAM 2, RAM 3 and RAM 4. So A11, A12, A13 are going to be going as select inputs. A14 to A19 are going to go as enable inputs. So since we have used all address lines, this kind of addressing scheme is called as absolute addressing. Now of course what happens is we are only going to have 4 memory chips available. So since we have 4 memory chips available, it is not necessary that you make use of all the address lines. What you need to do is you just need to select between these 4 memory chips. So it is not necessary that all address lines should be used. And other alternative design could be that I'm only using the required address lines, that is A11 and A12, which distinguish between RAM 1, RAM 2, RAM 3 and RAM 4. A is always going to be 0. So only one of these is going to be selected, and LS138 is always going to be enabled because G1 is connected to the 5 volts. G2 A bar and G2 B bar are going to be connected to ground. Now I'm only using the address lines which are required to select between RAM 1, RAM 2, RAM 3 and RAM 4. So this kind of addressing is called as incremental addressing. So where you are going to make use of only those address lines which are actually required to distinguish between the 4 memory chips. So what we attempted to do here was to connect 8K of memory to 8088. So just let's quickly review what are the different steps that you have to follow. The first thing that you have to do is you have 8K of memory and you have 2K chips. So you have to see how many chips you have to connect. To get 8K of memory, you're going to require 4 2K chips. So since you have 4 chips, you have to allocate a set of addresses to each one of these chips. This is called as memory mapping, where you give a set of addresses to a chip. How many addresses you have to give depends upon the size of the chip. It is going to be a 2K chip. So you have to give 2K of addresses to each chip. So RAM 1 here is going to get the first 2K of addresses. The second 2K address block, that is 0800 to 0FF, is given to RAM 2. The next 2K block is given to RAM 3. The final 2K block is going to be given to RAM 4. You can see that only 8K of memory is there. So you have memory starting from address 000 to 01FF. The only thing is it's distributed between the 4 RAM chips. Now once you have done that, you have to do the memory interfacing. So to do the memory interfacing, we have to see what signals have to be connected. The control signals are straightforward. You have to connect the read and write control signals to memory read, memory write. The data bus of the CPU gets connected to the data bus of the memory. There's going to be no problem in that because the data bus of 8088 is going to be 8-bit. The data bus of memory is also going to be 8 bits. So just connect the data bus. Then we have to connect the address. how many address lines are we going to require? It's a 2K chip, so you're going to require 11 address lines. So A0 to A10 of the CPU will be connected to the 11 address lines of memory. So A0 to A10 from A0 to A10 of the CPU. What do I do with the rest of the address lines? I use it for selecting the RAM chips. So I have to select one of the 4 RAM chips. How do we select the RAM chips? For that we are going to make use of a 3:8 decoder, which is LS138. To that you have to provide the select signals and enable signals. The output are going to be connected to the chip select of the RAM chips. It becomes easy to connect because if you see here, the outputs are going to be low active. The chip select of the memory is also going to be low active, as you can see here. So you don't require any inversion. It becomes easy to connect. So before you connect, you just have to examine the address lines a little more carefully. So the address lines A0 to A15 have been expanded. We have to decide which address lines we are going to use. Of course, we cannot use A0 to A10 because they are already going to the RAM chip to select one of the memory locations. We have to select the other address lines. If you look at that, 13, 14, 15 are going to be 0 for all 4 RAM chips. That leaves us with using A11 and A12 to select between RAM 1, RAM 2, RAM 3 and RAM 4. So in the first kind of addressing, which we called as absolute addressing, we made use of all the address lines. So A13, A12 and A11 were made use for selecting the RAM chips. So if it is going to be 000, then RAM 1 is selected, 001, RAM 2 is selected, 010, RAM 3 and 011, RAM 4. So we made use of A11, A12, A13 to select one of the RAM chips. The rest of the address lines were used for enabling the decoder. A14, A15 always low, decoder G2A bar, G2B bar. A16, A19 were connected to a NOR gate. Simple reason, the NOR gate is the only gate which will give you a high output when all the inputs are going to be low. So when A16 to A19 all are going to be low, only then the output of the NOR gate is going to be high. So this goes as G1. So this is going to be what is called as absolute addressing, where you make use of all address lines starting from A0 to A19. Now it is not necessary you make use of all of them, because according to our memory map, what we require is only A11 and A12 to select between the RAM chips. So instead of using absolute addressing, you can also do incremental addressing, where you use only A11 and A12 to select between RAM 1, RAM 2, RAM 3 and RAM 4. So this kind of addressing, where you're going to use only the required address lines, is called as incremental addressing. Now generally we use absolute addressing with most general purpose systems, but then if you want to decide whether you want to use absolute addressing or incremental addressing, in most cases it will be specified whether you have to use absolute or incremental. But in most general purpose computing systems, because you can keep on adding memory in general purpose computing systems, an absolute addressing scheme would be preferred, where you are making use of all address lines, because later you might be adding more memory chips. This addressing scheme will work only if I have 4 memory chips, whereas if I use absolute addressing, later it becomes easy for me to actually expand my memory. So if I'm thinking of a general purpose system, generally we go on and expand memory. So it's preferred that you use absolute addressing scheme. That is the previous addressing scheme where we made use of all the address lines. So later if I want, I can connect other RAM chips to output 4, output 5, output 6 and 7, because I made use of all address lines here. So this is how you actually can connect a memory chip to 8088. So we saw that with an example how to connect an 8K chip. So the first step is decide on the number of chips. The second step is do the memory mapping. The third is to design the decoding logic. So we'll stop with this in this session. In the future sessions, we'll see more examples of how to connect memory chips to 8088 as well as to the other processors.